Welcome to Easy Math TV. This is the second video in our short little series here on the Poisson distribution. This is the second special kind of probability distribution that is discrete that comes up in our course. The first one was the binomial distribution, and prior to that, we just introduced you to the idea of a probability distribution for a population and for certain types of random variables. So let's dig in. In the video right before this one, which I'm calling part one, I explained to you what the Poisson distribution is and what the requirements are. So if you have not seen that video, you'll want to go back and review that and put into your notes what the requirements are for the Poisson distribution, because that's going to come up in some of the exercises, and it'll be part of your quiz questions as well. So, but for right now, for this video, I want to just do a couple of examples so that you can see, how do we solve problems that involve the Poisson random variable. So the first example, and these are just word problems here. First example, a company has 7,000 arrivals of internet traffic over a period of 17,030 thousandths of a minute. So we're talking about computers here. So computer calculations take place over thousandths of a minute, very small intervals of time. And this particular company has probably thousands of computers all on the internet. And when they calculate how much communication is happening over the internet with those computers, they have calculated that there are 7,000 arrivals of traffic, so just electronic communication, over a period of that this number of thousandths of a minute, so 17,030. And then we're letting the random variable x represent the number of such internet traffic arrivals in 1,000th of a minute. So instead of 17,030, we want to break it down into just how much traffic is happening over 1,000th of a minute. And then we're being told it appears that these internet arrivals have a Poisson distribution. So there is an algebraic formula that helps us to calculate Poisson probabilities. I'm just going to kind of put a box around this formula that you see here, right there. And let's change the fill to no fill. So that formula is used like just on a scientific calculator. You can use that formula to calculate probabilities of any outcome X. Fortunately, though, we have software that we're going to be using, so we will not be using that formula, but I just wanted to show it to you just so that you would know that, just be aware that it exists, that there is an algebraic formula for calculating Poisson probabilities. Okay? Let's read the rest of the question. We can use that formula to find the probability of exactly 2 arrivals. So that's one of our outcomes of X, okay? 2 arrivals in 1,000th of a minute. And what are the values of mu, X, and E that would be used in that formula? So we're not even being asked to use the formula. We're just being asked to identify what mu is, what is the value of X that we're interested in, and what is this E thing. So let's answer the question here. The expected value mu is just going to equal 7,000, which is our number of arrivals, divided by 17,030, which is the number of thousandths of a minute that we have data for. So we have to take that 7,000 and break it up by the 17,030, which means we're dividing. And mu then is equal to 0.411 if you round it to the thousand, to 3 decimal places. So it's approximately 0.411 arrivals per thousandth of a minute. Okay, that's an expected number. So that's what mu means, is this is the expected number of arrivals per thousandth of a minute. Okay, and that's all that we're being asked to do there for mu. And then it asks for the value of x. So this is basically just how do you understand what the problem is asking. So the value of x is the desired number of arrivals. So what is the desired number of arrivals? Right here, we can see that right here where it says probability of exactly 2 arrivals. So basically, that's what we're being asked to identify, like probability that x is equal to 2. So x is 2. And then E is called Euler's constant. And if you type that onto a calculator, you actually have a key on your calculator for the Euler's constant E. But I'm just going to give it to you here. So anytime anybody asks you what is the value of E, you can just say, oh, it's approximately equal to 2.71828. So that's taking it out to 5 decimal places. You can round that to any number of decimal places that is being asked for. But so if you were to round it to 3 decimal places, it would be 2.718. If you were rounding it to 2 decimal places after the decimal, it would be 2.72. Okay? So that's called Euler's constant, and that does not change no matter what the problem is that you're dealing with. So those are the 3 things that you would have to plug into that formula there if you were actually just using a calculator to calculate the probabilities. But we're going to be using StatCrunch. As a general rule, that's what we're going to be using. So let's look at example 2 here. Example 2 says the random variable x, which really should be a capital X, by the way, represents the number of phone calls an author receives in a day, and it has a Poisson distribution with a mean of 6.7 calls. What are the possible values of x? Is a value of x equals 2.3 possible? And then the third question is x a discrete random variable or a continuous random variable? So it looks like with this exercise or example, we're still not being asked to calculate anything. We're just being asked to identify or interpret what we're seeing here. So the first question was, what are the possible values of x? So that has nothing to do with the 6.7 here. X is Poisson, so we're being told that it's a Poisson distribution. Therefore, x has to be, in brackets, I have 0, 1, 2, 3, etc., etc. So you need 3 dots after that. So there is no upper limit to the values of x. X starts at 0, and it counts by whole numbers on up to infinity. And that's just what x is by definition of what the Poisson distribution is. So that helps us to answer the next question. Is a value of x equals 2.3 possible? And so we can honestly say that it's not, because you look at capital X, and it's got to be whole numbers, 0, 1, 2, 3 on. So 2.3 is not possible. And the reason, again, for that is because, and this is the answer to the third question, is x a discrete random variable or a continuous random variable? And the answer is x is a discrete random variable. So those 2 parts were actually kind of connected there. A value of 2.3 is not possible because it's a decimal and it's not a whole number, and that goes along with this fact that x is a discrete random variable that takes on only whole number values. Okay, so that was just kind of a concept question. Example 3, though, we actually are going to have some calculating to do here, and then with the fourth example as well. So example 3 says, assume that the Poisson distribution applies and that the mean number of hurricanes in a certain year or a certain area is 6.7 per year. So there's the 6.7 again. And our interval, our time interval that we're interested in is per year. And we're confining ourselves to a specific geographic location. Okay? So that's not the interval. The interval is per year, and it's 6.7 hurricanes. So part A asks the question, find the probability that in 1 year there will be 5 hurricanes. And before we read part B, to find any probability that involves the Poisson distribution, we're going to be using StatCrunch, and we go to Stat, Calculators, and Poisson. And the directions here say we're going to type in the mean, so that's our 6.7, and then we're going to choose probability of x equals 5. So I want to show you, for just this one example, what that actually looks like. So if we go to Stat, Calculators, Poisson, here we are. The mean just kind of defaults to 10, so we're going to put the 6.7 in, and then the probability kind of defaults to probability of x less than or equal to some number, but we need to change that to equals because we're only interested in the probability that x is exactly equal to 5. So, and then I have to calculate. So you click on compute, and you actually will see a graph of all of the individual probabilities. This is our probability distribution bar graph. Okay. It's just a bar graph that shows us all the probabilities for each outcome. And you'll notice that the one we're interested in is actually highlighted in red. And it's up here little less than 0.15, and we can actually see the number in the box. So it's 0.13849,042, you know. So that's our probability of x equals 5. So up here in my document now, I hit compute. So this is the probability per year. So in any year, what's the probability of 5 hurricanes? 0.13849, so I just rounded it to 4 decimal values. Okay, so that's my answer to part A. Part B is now a follow-up question. What about not just 1 year, but in a 35-year period, how many years do we expect to have 5 hurricanes? So we're taking that, what we need to do for that is take our answer that we just got, the probability of having 5 hurricanes in a year, and multiply that by the 35 years, distributed across the 35 years. So basically multiply the probability we just calculated by 35. Because we're just interested in the 5 hurricanes, and we're talking about independent events. So we're multiplying by across the 35 years. 0.13849 times 35 just happens to equal 4.85 years. So basically what that is saying is that we can expect to see 5 hurricanes in about approximately 4.85 years out of 35 years. So if you're looking at a 35-year period, we would kind of expect to have 5 hurricanes on average in about 4.85 years. And that's just an approximation now. So there's a third part to the question. Part C is following up with that. How does the result from part B, which we just calculated as 4.85, compare to a recent period of 35 years in which 4 years had 5 hurricanes? And then does the Poisson distribution still work well here? So our answer is we expect to have 5 hurricanes in about 4.8 out of 35 years. That's what we just calculated. 4.8 out of 35 years. But that's kind of an average. So the recent period of 35 years, which saw 4 years with 5 hurricanes, is relatively close to that. Okay? So how does the number 4 compare with the 4.8 is what we're being asked, really. So our conclusion is that 4 years is close to 4.8. Okay, it's close enough. And so the Poisson distribution does work well in this situation. And that's our conclusion for that problem. All right. Expected values are, expected outcomes. There's always going to be some, some fluctuation from that. And then our final example, and I'm not going to go into show you this in StatCrunch. I'm going to just tell you that you can actually type it into StatCrunch and get an answer. Our last example, in a recent year of 365 days, a hospital had 5,784 births. So there's a 3-part question here. Part A is asking, find the mean number of births per day. So to do that, that's our mu. We're calculating mu. So births per day means you have to start with the number of births and divide by the number of days. Births per day, number of births divided by number of days. So that's 5,784 divided by 365, which gives us 15.8 births per day on average. Okay. Part B, find the probability that in a single day there are 17 births. So now we need to go into StatCrunch because we're being asked for an actual probability. Okay, so use our Poisson calculator and type in our mean of 15.8. And then in the other box, we want probability parenthesis x equals 17, close parenthesis, and then calculate compute, or press the button or click on the button compute. And this is the number that we get. We get 0.092097778, which we're going to round to 0.092. Okay, so that's our answer to part B using the StatCrunch calculator for the Poisson distribution. Part C then, find the probability that in a single day there are no births. So no births means 0. Okay, so the probability of x equals 0 is this number you see here, which there's a lot of zeros that come after the decimal. So when you round it, you're just going to round it to 0. Even though it's really, the probability is kind of 0 plus, it's like, it's not quite 0, but it effectively is when you round it to 3 or 4 decimal places. And then the last question, is this number of births in a day significantly low for this hospital? And the answer would be yes, because the probability is much less than 0.05. So when the probability is that low, we say that that number of births would be significantly low, okay? Or that result, that X value is significantly low because its probability is very, very small, okay? So that's kind of problem solving with the Poisson distribution. And I hope you will like, subscribe, comment down below with these videos if you find them useful or if you have any questions for me. And I'll see you in the next video.